the June Air oilless rocking piston air compressor that uses a two-stage design to compress intake into roughly 10 to 12 times the original pressure. But how does it actually work? A 24-pole electric motor rotates a center shaft and articulates two counter-rotating pistons associated with the cooling fans. Starting at the entrance, during the intake stroke, a one-way valve takes in airflow, and then it goes into the first stage cylinder, which has a larger diameter than the second stage one. This is typically what's considered a low-pressure stage. As the piston travels up and compresses this air, the intake pressure valve closes and the exit pressure valve opens. The pressurized airflow goes through the exit valve, through a tube, and then into stage 2 high-pressure cylinder. As the pistons are mounted 180 degrees apart, the exhaust stroke of the stage 1 piston is also the intake stroke of stage 2. As the piston 2 travels up and compresses the gas even further, the intake valve of the second stage is closed and the exit valve is open. The pressurized gas then leaves the system after being compressed twice. To quantify some performance metrics, we'll utilize pressure calculations and mass flow rate calculations. To make these calculations possible, we want to start by defining some models and assumptions. We're assuming our fluid is a compressible ideal gas, as the compressor doesn't compress air to extremely high pressure or low temperature. This implies that the intermolecular interactions affect the system significantly less than the kinetic energy of the gas molecules themselves. We're assuming the gas is isentropic, as that would simplify calculations, and it's reasonable to use adiabatic and reversible assumptions in these ideal contexts. To determine the compression metric, we start with the ideal gas law. We define the inlet and exit pressure ratio as ρ1 RT over ρ2 RT. And assuming the isentropic process, we can cancel out the constant RT term. Writing out the density as mass over volume, as mass is conserved, the diameter of the piston head remains constant over time, and pi remains the same. This allows all values to be canceled out, leaving only stroke distances. We now arrived at pressure out is equal to pressure in times the bottom stroke distance over the top stroke distance, which equals pressure in times the compression ratio. The intake pressure is assumed to be ambient, about 1 bar, and the pressure ratio is given by the piston head position at the bottom of its stroke over its top position. Steps to find the compression ratio for the second stage are identical, and we can calculate the total effective compression ratio of the system by multiplying the two independent stages' compression ratios together.
In our specific example, we are plugging in each of the piston heights and subtracting by how far each cylinder is recessed to get each piston's stroke length. These values reduce to 17.29. This number, after taking into account reductions due to losses that will be discussed later, makes sense considering the specified 10 to 12 bar pressurization from the manufacturer. To determine the mass flow rate, we write mass as density times volume over the time for the shaft to rotate 1 revolution, and expand out the density term using the ideal gas relation such that we see the mass flow rate is proportional to the piston diameter squared and the stroke length.
To analyze the Reynolds number, we can utilize the mean flow approximation. We'll use the volumetric flow rate and the area of the piston head to find the velocity, since the mass flow rate entering the system is the same as the mass flow rate leaving the system. We're ignoring the temperature's influence on the term. By acquiring the volumetric flow rate from the tech sheet, we obtain an approximate Reynolds number of 1,719. A Reynolds number that's too much lower than this would prevent the cylinder from filling entirely and would hence reduce efficiency. But if the Reynolds number was too much higher, there would also be more wear and friction losses, also reducing the system's efficiency. Efficiency and mass flow rate losses are also caused by viscous losses within the transfer tube between the two cylinders. This viscous loss is dependent on the calculated Reynolds number. The Reynolds number of this system changes with time as the pressure and temperature changes with the compression. However, the main part we care about is when the air transfers to the second piston. Thus, we can take the pressure and temperature of the state of the air at the end of the compression stroke and use those values. Our results show that it's reasonable to neglect the viscous effects on our ideal model analysis. Now that we understand how the two-stage pump works, we can apply our newly acquired knowledge towards making interesting fluid machines in the future.